Okay, ladies and gentlemen, in today's video, what we're going to be talking about is primarily simplifying radical numbers, which is a skill that typically you learn how to do in geometry. Students now are starting to learn how to do it towards the end of Algebra 1. You should have seen uh, this particular skill in geometry and again in Algebra 2, particularly when you're working with your unit on quadratic functions, because the quadratic formula has that square root portion of it, and you have to be able to simplify it in order to determine, uh, whether or not, that's where you saw if you had a negative number underneath the radical, and that again, that's just one of the skills that you would have practiced in order to simplify the quadratic formula to its most simple form. So again, just kind of keep in mind the square root of -1 does equal a the imaginary number I. And there's two ways that I'm going to kind of remind you on how to simplify a radical number. And, I'll show you both ways here in just a second. But make sure you get all the steps copied down into your notes. And let's take a look at some examples. So here we have 4 different examples of how to, of radical numbers that we want to try and simplify. Now you can tell here in example A that because of the negative sign underneath the square root, that should produce an imaginary number. So let's break it up into its proper components so we can kind of see why we're doing what we're doing. The square root of -81, underneath the radical symbol, the -1 is the product of a couple of numbers, 81 and the number -1. Well, the square root of 81 itself is a perfect square number. That is going to give me a 9. Positive or negative, but we'll just stick with the primary answer as being a positive number. And the square root of -1 is just I, so when I simplify that particular number, all we're left with is a 9i. So here, the square root of 98, this one is a relatively nice one to look at as far as how we simplify it. I want to go ahead and show you 2 ways. This way is known as a factor tree, and basically what you do is you kind of start with the smallest number that you can as a factor of the number that you're working with, in this case 98. So the smallest factor of 98 is the number 2. So I put a 2 here and I say, okay, how many times does 2 go into 98? And I would say, oh, well, it'll go into 98 49 times. And I would kind of continue with the smallest number. So 2 does not, unfortunately, go into 49. 3 doesn't work, 4 doesn't work, 5 doesn't work, 6 doesn't work. So the next factor for the 49 is actually a 7. And 7 goes into 49, well, 7 times. 49 happens to be a perfect square number. Now, when you're doing a factor tree like this, what you're doing is you're looking for factors that are in pairs. So here I have a factor of 2, but it's the only one that I used. And here I have 2 factors of 7. So that's a pair. And so that tells me that pair, it's going to come out of the radical symbol, and I'm going to have a 7 on the outside of a square root. Well, the remaining terms underneath the square root symbol are going to be whatever factors that we could not take out. And so that would give me 7 radical 2. Now the factor tree is a great way of doing it. Some other people will do it in an opposite order. They'll build it from the bottom up and they'll call it like a wedding cake because it kind of looks like a wedding cake where the biggest layer is on the bottom and you got a slightly smaller layer on the top and each time it goes up. Now the factor tree personally is not my favorite method of simplifying a radical number. I like to think of just perfect squares, meaning perfect squares are 4, 9, 16, 25, etc. Those are the perfect square numbers because if I take a square root of it, it'll give me a whole number. So this one is relatively easy to kind of see, especially looking at the factor tree the way we did the first time. If I break up what I would do normally is I would think, what's the biggest perfect square number that would go into 98? And well, in this case, 49 goes into 98 pretty easily, and I would multiply that by 2. And so all I'm looking at is what's the largest perfect square. I take the square root of that number, and since the 2 I can't take the square root of that, it stays underneath the radical. And either way is an appropriate way of looking at how we would simplify a radical number. So here we have 3 multiplied to the square root of negative 144. So we'll look at this kind of like this. Again, we'll leave the 3 on the outside of the radical, and the 144 is really the product of 144 times negative 1. So most of us are going to recognize pretty quick that the 144 is really just, if I take the square root of that, that's going to give me the number 12. And the square root of the negative 1 is going to give me an I. Now the 3 that's in front of the square root symbol already, it's going to be multiplied to whatever we get there. So here I'm going to say 3 times 12, because that's what the square root of 144 gives me, and the square root of negative 1 is going to give me I. Now even though I is an imaginary number, it kind of has that 12 as a coefficient, and the 12 is a real number. So the 3 and the 12 will actually get multiplied together to give me 36I, and that would be the simplified answer on that one. And this last one here, again, it's kind of like saying here we have a negative 1 multiplied to the square root of negative 75. So again, I'm going to look at the 75 as a factor tree, just in case you need to see it again. So the smallest factor of the number 75 happens to be a 5. And 5 will go into 75 15 times. And now I'm going to kind of look at this one here. The smallest factor of 15 is a 3. And if I multiply that by 5, that would give me a 15. Now you see here, I have 2 5s. Those are 2 factors that produce the number 75, with this 3 being the lone factor left over. So the square root of 75 is also just 5 radical 3. Now keep in mind it was the square root of negative 75, so this is really that, and it was multiplied to a negative 1, so that would be our final answer that way, looking at it as a factor tree. Personally, I'm not a big fan of the factor tree, but if you like it, please go ahead and use it. I like to just think of it as what's the biggest perfect square number that will go into the radicand, the number underneath the square root. So the largest perfect square number of 75 is 25. So I can say 25 times 3, and of course there's a, oops, not an I, I'm getting ahead of myself, there's a negative 1 there. So I'm going to just write out the individual factors of the negative 75. So the square root of the 25, well, that'll give me a 5. The square root of the negative 1, that'll give me an I. And since 3 is not a perfect square number, it stays underneath the square root symbol. And either way, I get the same result. So a couple more examples to take a look at here, just simplifying radical numbers. Square root of negative 17, well, again, that is a combination of 17 and the number negative 1. Now 17 happens to be a prime number. It does not have any perfect square factors. So the only thing I can take the square root of is the negative 1 in this case. So I will wind up with I times the square root of 17 as the final simplified number. And kind of the same thing on the next one here. 53 isn't a prime number, but it's also not really a composite, is what we would think of as a composite number, but it doesn't have any perfect square factors to it. So if we look at the individual factors, I have 53 times negative 1. Now 53 doesn't have any perfect square factors to it, so the only thing I can take the square root of here is the negative 1, so that'll give me I times the square root of 53. Moving on to the next example, here they're giving us fraction underneath the square root symbol. Now, personally, and this is something that does tend to throw students off sometimes, I prefer to see a problem such as this written with discrete radicals in the numerator and the denominator. It just seems to look uh, more appropriate for students to recognize that we have to try to simplify the numerator as a radical and the denominator as a radical. So looking at the square root of 45 in the numerator, I'm going to say, well, just looking at the largest perfect square number of 45 is 9. So 9 times 5 will give me a 45, and if I multiply that by a -1, I'd get the -45. The square root of 36 in the denominator, that is a perfect square, so I'm going to just go ahead and say, oops, I want to write 36 again. Square root of 36 is just going to give me 6. So let's go ahead and continue simplifying what we have in the numerator. The square root of 9 is going to give me a 3. The square root of the -1 is going to give me an I. And the square root of 5 doesn't simplify, so it stays radical 5. And all of that is over 6. Now here I have 3 times I times the square root of -5 over 6. The 3 and the 6 can simplify. 3 goes in 6 2 times, so that'll give me just I radical 5 over 2. And that would be the final simplified answer on that one. And lastly, again, I prefer to think of it as an individual radical in the numerator and the denominator. It just, makes more sense to me. It generally makes more sense to students to see, well, I do have to take the numerator and simplify it and the denominator and simplify it. Now, if there is a common factor between the numerator and the denominator, we can simplify it that way as well, like a normal fraction. But I'm going to go ahead and just kind of stick with this way. So in the numerator, -49 is the product of a 49 and a -1. In the denominator, largest perfect square factor, 75, we've already seen this one, is 25 times 3. Well, the square root of 49 in the numerator, that'll give me 7. The square root of -1 in the numerator will give me an I. In the denominator, the square root of 25 will give me 5. And I'm still left with a radical 3 that doesn't simplify, and the 5 in the denominator and the 7 in the numerator are not, they don't have any common factors, so we can't simplify those at all. So that is what we're left with as our final result here, 7I over 5 square root 3. So the next thing that this is kind of leading to, because simplifying radical numbers is something, again, that you would have seen in your quadratic functions unit in Algebra 2. This is where in our course, College Algebra, we're going to start working a little bit more with complex numbers. Now, we've already seen that complex numbers come in the form of a plus bi, where a is a real part, I, that's the imaginary part, and this b is also kind of a real coefficient that's going to be multiplied to the negative, or to the imaginary number. So again, copy down the examples here as far as step-by-step stuff. Rewrite any radicals that you have with their respective factors. Simplify it as much as you can, and see what you wind up with here. Now, the one thing that this is going to ask us to do specifically is identify what is the value of A and what is the value of B when we have a number written in complex form. So let's take a look at these examples. We have 4 plus 3 times the square root of -20, and all of that is over 2. So taking what we've seen, I'm going to rewrite the 20 with its factors. Now again, if you want to use a factor tree, by all means, use a factor tree. I'm going to continue using the perfect square numbers. The largest perfect square that goes into 20 is 4. The other factor would be a 5, and all of that has to be multiplied to a -1. And we'll just write that over 2. So let's just keep simplifying the radical. I get 4 plus 3. Oops. Let me back up just a hair. So that 3 is there. Now the 3 is multiplied to all of the radical stuff that's there. Everything that's underneath the radical symbol or anything that we take out. So the square root of the 4 will give me a 2. So I have to multiply it to the 3 that's already there. The square root of the -1 gives me an I. And the 5 doesn't simplify as a square root, so it stays radical 5. And we'd say over 2. Now at this point, some of you may notice the 2 is a common denominator to the 4 and to the 3 times 2i. And you can probably see that this 2 here and this 2 here will simplify. And the 2 and the 4 will also simplify. So that will give me 2 plus 3i radical 5. Now, if you wanted to, you could certainly multiply it through and make the 6i in the numerator. But again, the 2 simplifies to both terms in the numerator. And either way, we'll wind up with 2 plus 3i with the square root of 5 left over. Now here, it is asking us to identify our a and b terms. So in this case, a is 2 and b would be 3 radical 5. The only thing that's imaginary is the I itself, and so we don't write it as the b value. It's just the numerical part. So let's try this next example. 6 minus the square root of -72 over 4. So 6 minus, we're going to start by breaking up the 72 with its proper factors. So the largest perfect square factor of 72 is a 36. So if I say 36 times 2, that will give me a 72. And if I multiply that by -1, that will give me my -72. And all of that is over 4. So simplify the numerator a little bit more. 6 minus the square root of the 36 will give me a 6. The square root of the -1 will give me an I. And the square root of 2 is not a perfect square number, so it stays in a radical form. And all of that is over 4. Now again, the 4 is a common denominator to this 6 here on the left and to the -6i more towards the right. So the 4 and both terms that have a 6 will simplify. So 6 over 4 simplifies to be 3 over 2. And 6 over 4 again simplifies to be 3 over 2. So we wind up with 3 minus 3i squared root of 2 as our simplified form of that number. And again, the a term is going to be 3 over 2. The b term will be -3 radical 2 over 2. Okay, sorry guys if I had to pause there for a second, but I had had somebody come into my room that needed to ask me a question. So let's go ahead and finish wrapping up this video here because we are about done with it. The last thing that we're going to look at are these 4 examples where again we just want to simplify it, write it in the form of a complex number, a plus bi, and say what the values of a and b are. Well, -2, well, that doesn't simplify at all, but it is an integer. It is a real number. So if we write it in the form of a complex number, we're going to say -2 plus 0i. So a would be -2 and b would be 0. Now here, -4 and I, that is going to give me 0 minus 4i in a complex form. A will be 0 in this case. B would be the -4. Here, the only thing that we're taking the radical of is the numerator. So I'm going to spread that out with its individual factors. 25 and 3 and a negative 1, and all of that is over 15. So the square root of 25 in the numerator gives me 5i after I take the square root of the negative 1 with the remaining radical 3 over 15. And the 5 and the 15, they have a common factor of 5, so that would give me I radical 3 over 3. And if we write it in complex form, we're going to say a 0 out here. So A would be a 0, and the complex, or the real part of the complex term would be radical 3 over 3. And last one here, negative 2 plus the factors of 48. The largest perfect square factor of 48 is 16, which would 16 times 3 will give me 48. And if I multiply that by negative 1, that will give me the negative 48 in the radical. Oops, and I don't know why I'm putting this isn't a fraction. Let me get rid of this here. Thinking of our previous examples. So negative 2 plus the square root of 16 will give me 4. The square root of the negative 1 will give me I. And the square root of 3 doesn't simplify. And so that's what we're left with as our simplified answer here, where A is negative 2 and the B will be 4 radical 3. All right, ladies and gentlemen, I hope you guys took some good notes. This is going to be coming up in some upcoming homework assignments, and of course quizzes and tests as they're approaching. So if you have any questions, make sure you have them written down. Come by, see me, before class, or when we start class,